For those of you that are into crossword puzzles, Kevin Rowland has put that desire in many of you, as he likes to do crossword puzzles. I would encourage you to work this one. It's not a terribly complicated one. In fact, it's kind of easy. But again, I encourage you to try it. And again, just like the previous days, comic strip, if you want to know the answers to this one, you may come and look on the door of my classroom. 5.4. The fundamental theorem of calculus. Ladies and gentlemen, you're talking about objectives and standards from calculus. What are the most important? This is certainly to be listed in the top 3. Today, we're going to talk about how we use the fundamental theorem of calculus. We will graph a function defined by integrals, and then we will find the derivative of a function defined by an integral. Again, I cannot emphasize enough the importance of today's standard, the fundamental theorem of calculus, as it opens up so many other things and has so many applications in calculus. Alright, well, let's start with it. It is so important, it is so large, in fact, we're going to break it up into 2 parts. Let's just look at part A. If f is continuous on a closed interval AB, then the function capital F of x, remember capital F represents an antiderivative, from a to x of f of t dt has a derivative at every point x in AB, and the derivative of that antiderivative is found by doing this right here, just taking the derivative of the integral, and it just equals f of x. Now, let me make a few comments about what's going to happen here. First of all, if we just look at the summation, here's the summary of it. Let me remind you from the last lesson that derivatives and integrals are inverses. They cancel each other out. But essentially what's going to happen here is this t-defined function is going to become an x-defined function, f of x. Now there are a few other parts here that we need to add in that are not going to appear on the screen, and I'll see if I can use a marker to make this happen. First of all, this works if this number right here is in fact a number, a constant. In fact, one of them needs to be a constant. If the top one is a constant and the bottom one is a variable, this still works, but also remember from the last lesson it makes the answer negative when you flip-flop the limits of integration. The other thing is this works here if this is just x. Now we can make it work also if it's not just an x, but what you would have to do, oh, sorry, I hit the wrong thing. Let me pause here and then back it up a little bit, or at least just back it up. Let me go back. There we go. Sorry about that. But as I was saying, what you would need to include in here, if this were something like a 2x or an x squared or a 5x, is you would need to include the derivative of that x, and hopefully we'll see some of those. So let's take a look. Apply the fundamental theorem of calculus. It says find the following using the fundamental theorem. We are taking the derivative of the integral of cosine t dt. Well, first of all, I see that this is just an x. I see that this is a constant. Now it's a pi constant, but it's still just a constant. So the fundamental theorem applies. All I have to do is I have to plug x in here, and that one doesn't matter. Now you may ask why this one doesn't matter. Why does a constant not matter? Well, think about if I were to take the integral of this. If I were to take the integral of this, I would have a cosine of x. Or I would have an antiderivative of cosine x. But then when I took the derivative of the antiderivative, it would just take it back to cosine x. If when I did this part, though, when I took the antiderivative and I plugged in pi, I would get a constant term. And when you took the derivative of a constant term, that constant term then goes to 0. And that's why you don't have anything out here. Alright, here we have the same situation. We have a constant term to a variable x. The derivative and integral cancel out, and you just have 1 over 1 plus x squared. Alright. Here now is one, though, that's a little different, like what I had mentioned. You see we have a constant term here, but this time we have an x squared. Now, if I were to take the derivative of this, which I'm going to take the derivative, it's still going to cancel out the integral. But on this one, it's not just enough to plug the x squared into the t here, which I'm going to have to do. But by the chain rule, remember when we do derivatives of the chain rule, I also have to take the derivative of that inside part, which would be x squared, And so what I end up with is, if you can just bear with me, this right here. Now, that's a lot of jumbled mess in here, but basically it's saying what I'm saying here. It's telling me that I've got to not only just take the derivative of the integral part here, but I have to take the derivative of the thing that you're plugging in. That is the chain rule. And that being the case, plug in your x squared into cosine x squared, and then the derivative of x squared is 2x. Alright, let's move our screen back up here. Find the derivative of the following. We have the integral from x to 5 of 3t sine t dt, and then we have this one over here. So how are we going to do these problems? Well, first of all, I'll remind you again from the last lesson that all it takes is a negative here, and we can flip-flop our integrations back to what they should be. Now I have a constant term here. I have just x. The derivative of x is 1. So all I now have to do is plug in the x here and here. Negative 3x sine x. But how do I do one like this? There is no constant term. So we could throw up our hands in frustration and say it can't be done. Or we could do something like this. I'm going to take the integral from 0 to x squared of this minus the integral from 0 to 2x of this. I can do that. I am allowed to do that. Now, if you want to know exactly how that is done, I will refer you back to the additivity rule of the previous lesson. If that doesn't help you, then for time's sake, I'm not going to discuss it here. I will discuss it with you in class, but that's where it goes back to that additivity lesson. Okay? So here we have the integral from 0 to x squared of this part minus the integral from 0 to 2x of this part. Now I can take these and I can plug them in because I do have a constant term. However, by the chain rule, I must also include the derivatives of these top parts. So when I do this one, what's the derivative of x squared? I'll also need a 2x. When I do this one, I'll also need the derivative of 2x, which is 2. So that's where the 2x and the 2 come from. And we're done with that one. All right. Now this is an interesting problem, and you'll forgive me. The solution has already popped up down here, but that's okay. Find a function y equals f of x with derivative dy dx equals tangent x that satisfies this condition right here, f of 3 equals 5. So I'm looking for a function whose derivative is tangent with this condition right here. So I'm going to come down here and I'm going to make just a very simple function. Now you could say, well, what about secant this or tangent that or secant tangent this? You know those old formulas from when we did derivatives. But really that's just extra work. Why don't I just do this? I'll put in my integral because the derivative in the integral would cancel out. And I know I need to make it a constant term here and an x here. So a constant term and an x, just like that. But why did I pick 3? And how does that play into what we're doing up here? Well, the reason I picked 3 is because of this 3 right here. You see, this tells me if I plug in 3, I should get 5 out as an answer. Well, if I were to plug in 3 right here, right now, I'm going from 3 to 3. That is the 0 rule of integrals, and so that means that this whole thing is 0. I'm starting and stopping both at 3. I cover no space, I have no area. But because this is 0 and I want it to equal 5, that makes it a very easy fit, and I just add 5 right here. So now the integral from 3 to x of tangent t dt plus 5 satisfies this condition up here. That brings us to part B of the fundamental theorem of calculus, and this, ladies and gentlemen, is the huge application. And if I may just go ahead and skip down right here. Here it is. Of course, same thing up here. The integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a. This is huge. We actually did one like this in the last lesson. But what you did not realize then is that you are actually applying the fundamental theorem of calculus. Again, please do not forget these things, ladies and gentlemen. They are very, very, very important. So we take a look at this one. Evaluate the integral below using an antiderivative. Our goal is very simple. We are to find the antiderivative of x cubed and the antiderivative of 1. And into each of those we are to plug 3. And then we plug in negative 1. And then we subtract the 2 answers. So what is the antiderivative? Well, the antiderivative of x cubed is 1/4 x to the 4th. Well, how do I come up with that? Well, remember, when you're doing antiderivatives, you increase one on the exponent. And then we have to think about, well, if I'm doing the derivative, this 4 would come out front here, but you see I have no number out front here, so I needed something to offset that 4 that was coming out front. 1/4 will take care of that. And then the antiderivative of 1 is x. Now, here's my antiderivative. I will now plug in 3 into each of these, and I'll plug in -1. So there's my 3, 1/4 x to the 4th plus x right here. Same thing with -1. And henceforth, it's just a matter of simplifying all that. 93 over 4 plus 3 over 4 gives me 96 over 4, which is 24. If you want to verify that with your calculator, go right ahead. If you punch this into your calculator, it will give you an answer of 24. Alright. Example 6. Finding area using antiderivatives. Find the area of the region between the curve y equals 4 minus x squared and on the interval 0 to 3 and the x-axis. So here's the total area that we are going to look for. Now, first of all, I'm going to partition 0 to 3. I'm going to partition it off with the zeros of y. In other words, I'm going to break this up into two separate integrals. I'm going to take an integral from 0 to 2, because you see here 2 squared is 4, 4 minus 4 is 0, and from 2 to 3. I'm going to work two separate integrals. Then I'm going to integrate the function over each subinterval. So I'm going to have the integral from 0 to 2 of 4 minus x squared. That's a positive area, you see, it's above the x-axis. Well, the antiderivative of 4 is 4x. The antiderivative of x squared is 1/3 x cubed. We've worked that one before. That gives me an answer of, let me move the box down here a little bit, 16/3. Now do the same thing for 2 to 3. Alright, again, it's the same antiderivative, but this time I'll plug in 3 in the 2. So plug in 3 first, minus, then plug in 2. And this time we get -7/3. Again, why is it negative? Because it's an area that is underneath the curve. We'll add the absolute values then, because we'll want total area, not net area. So we'll consider both areas to be positive, and that gives us a total area of 23/3 underneath that curve. And how about that, ladies and gentlemen? It's the shortest lesson we've recorded so far. We're done already, and we still have a couple minutes left in the first video.